previously task 5, we will change the systematic code, group code to the cycling code, and the all subtasks will be the same. And in your individual parameters, let's check it here. And will this is my previous version, and you will get your name, and here you will see what error correction code you will do. And some people will have the cycling code, but as the Dr. Ennis mentioned, there is some mistake of the generator phenomena, but we can check it before we choose the phenomenon, use the function. So let's move to Octave, and firstly I will load the communication package. So what we will use for the cycling phenomena generator, the how to use this one. And here we can generate our phenomena, generate the phenomena, and we only needs to know your total bits and your data bits. So for example, here we have the total bits is the 31, which means our data bits will be the 26. Let's check it. And 31 and 26, and we can see all possible nation. So, and we can check it with the here Z5, Z4, which means the Z4, Z3, and we don't have the Z2, which means Z2 is 0, and the others will be the 1. So here we choose this one, and this is correct. So use the same way you can choose check your individual how to say your individual generated phenomena, and if it's not correct, you incorrect, you can correct it. This is what I want to see. So let's move to the cross project part, and we also have the how to say uh, the encoding for the sorry, let's move to here, and here we will do the step by step, and here same with previously calculation process, we need to know our code wordness, and it will given for in your individual parameters, and we will know our number of the check symbols, data symbols, and you already can get your generator phenomena, and we can how to say use the function to generate your encoding matrix and decoding matrix. So here we will use this one, Cyclic generator. Let's see how to use this. Use it here. If you want to use the generator, a cycling generator, we must need to use this one. For example, N is our code wordness, P is the generator phenomena. So let's do it. If in this case I have the total code wordness is 7, and here this is my generator phenomena, which is the 1 0 1 1. So let's do it. And accordingly, we can generate both encoding matrix and decoding matrix at the same time. So let's name it and uh, which will be so code coordinates is 7 and generate polynomial is the 1, 0, 1, and 1. Let's see. Ah, undefined. Ah, mistake here. As you can see here, we generate the both encoding matrix and the decoding matrix. For the encoding matrix, here its position is the different. We have uh, the E E3, E2, E1, and C4 to the C1. Here is identity matrix, and we need to here for the decoding matrix. Here we have the uh, check check symbol matrix, which is also the identity matrix. So we will need to do some change for this part. But firstly, let's come back to here. And we need to get our syndrome. However, use the syndrome, we need to use the arrow vector to do the division with the generator polynomial. But for here, we have the first three syndrome. The identity matrix for me is check here. The check symbol is 3 bits. So maximum is the can reach to here the E1. And for you, if you have the 5 bits check symbols, then you will get the identity matrix of the here we'll add the to the 5 bits with now, and we can go on with the to calculate the data and use the uh, arrow vector. Then we divide with divide by uh, the generate the polynomial. Then we can step by step to get the syndrome. So what we need for the data symbol data block, and you can similarly with the previous day group code, use your name, and here we only need 4 bits the data block. And if you have the like 26 data block, you can just repeat your name, then you can write down your data. So let's do it. First, we need to clear all, and for the binary data, here Dr. Allen's the data is 1011. I will need it changed with his previously data, but my data nance it's 4 bits. That will not change. 1, 1, 1. Yes, this is our user data. Next is the here we need to use the encoding matrix and the decoding matrix. However, we find that it's quite different with the position of the uh, check symbols and data symbols. We have to how do you say to change their position, rearrange the uh, this matrix, this both matrix. So firstly, we here we will same with the use this function, use the cyclic generator to generate the both uh, decoding matrix and encoding matrix. Encoding. So we have to change the control symbol and the data symbol positions. Now we can specify some position like here. In my case, which will be I hope to the how to say the data the data uh, symbols with the identity matrix before then the control symbols. And here also will be like this for the decoding matrix. So my data matrix will be from the 4 to the 7 uh, columns, and 4 to the 7, and my control control symbol matrix will be the first column, second column, and the third column. So it will be the 1, 2, 3 column. Then uh, we can let's do it, and we can use this index to change the position. So encoding matrix will be the encoding matrix, and followed by this index, which will be the according by the column. So we don't will change the row, and we will index all of the rows, and nothing will be changed. I name this as B. Let's see what's as you can see, the identity matrix of the data matrix changed in front of the control symbols here, and this is here, and this is here. So similarly, we will do this work for the decoding matrix. So next we will do the uh, encoding to generate the code word. So we can easily use the model, use the mode operation with the binary with our user data and encoding matrix. Let's see what will be the, and don't forget we do the mode operation, which will be the and no, multiplied with the encoding matrix and 2. Oh, sorry, I haven't. I forgot to type here. And you will see my here is my you will see the code word is generated, and it has total 7 bits, and the first 4 bits is my data symbols, and the last symbols will be my reminder, which will which is the put the reminder to the last 3 code word. So it's finished, and we can see, come back to the here. So first subtask is encoding and write your individual code word. So we finish this, and we will move to the decode part. Firstly is we have to decoding code words without errors, which we code. And we will move to the slides. And firstly, we need for the decoding process, we need the code wordness and the syndrome. So if the reminder is the 0, and which means no errors happened here, let's do it. And the syndrome will be the we need the code word multiplied with the decoding matrix. So here is mentioned about my position is wrong because here my code word is the dimension is the 1 multiplied 7, and the decoding matrix it has the 3 multiplied with the 7 dimensions. So I need to for the decoding matrix, I need to transpose it. Let's see with the decoding. Just prime it. So we can get the here with the E3, E2, and E1. Now we can do the now we can calculate the syndrome. And so here it shows the syndrome is the 000, so which means it has no error. Let's keep it as our so we finished the second subtask, which is the decoding code word without errors. The third subtask is the decoding code word after one single error. Let's do it. So if I want to let code word has one error position, I can use some easy method. Let's do it together. One error. So I will use the Randy, which means the maximum, the random generator, the position is the seventh 7. So it will generate from the 1 to 7 any of the number, and we will index this in our code word, and hope to can change uh, one of the bits to let it make one mistake. We will index this, and to change here code word. Let's see what will happen here. So here is the previously code word. We have the 111010, and you will see here the data block. The data block changed at the fourth position, right? Here previous we have 0, and now we change the 0 to 1, which means there is 1 errors happened. So let's do the decode. What will happen with, let's rename as the syndrome, because it will generate a new syndrome. Code word start with the decoding matrix. So just run group code and here, which is and I have a mistake here, which okay, but we can do it at here. Okay, syndrome. Operators argument.
But it looks like your matrix hasn't been transposed. It's problem there. Or maybe you have transposed it double times.
Yes, I already. I think my here I should put in here. Yeah. So yes, it's good to do the transpose before after you rearrange the encoding and decoding matrix, and you have to do the transpose after you rearrange the position. So now we got the new syndrome, which is the 101. Now we can come back to the syndrome table 101, which is the C1, which is the first bit. You will see here, and there is one mistake here, and the new syndrome find the correct error position at the C1, and the others will see nothing more changed here. For this is for the single error situation. So if there are two double error happens, let's check it. And we need to change like so A is the only change the one position. Now we can change the second position. Use the same way to randomize this, which means if it can if it will change this code word, which means already changed the one code one symbol result, which means one error happened. After that, we will change another symbols to generate one more error. So code word will be the index will be the B. And syndrome, we will get new syndrome name with C. And here, this is the no errors happened, and this is one error happened. So after each time, it will generate a different position arrow. So you will see here, this is the six position, which is the 0, 1, 0, 1, 0, which means let's check the table 0, 1, 0, which is the A6. And for here, A6, and we still have to change one, which is as the 0, 0, 1, 0, 0, 1 at the A7. However, it's 0, 0, 1 at the A7, which means the here. However, it's not. It's only it changed as the 4 position here. So if two errors happened, then the syndrome will show the incorrect position. So if so, we can keep going with the how to if the 3 errors happened, which will what will happen. And for the here, same with the code word. Syndrome. To multiply with the decode. We can write. So, and you will see it changed at the same position. So, which means there is the B is the 7 and C also is step 7. So B shows the 101, 101 is the A1. However, A1 is no mistake and it is A7 mistake, and it shows the signal 3 shows 100, which is the A5. And it's still uh, the A1. Yeah, here is A1, and it still shows the A1. So, if the 3 errors happen, the syndrome will still show the incorrect position. So that means the Hamming cycling code also can detect the one correct errors and can detect the one errors, and it can detect the 2 errors, but it can only correct one errors. So this is decoding after the double sim. I already showed you after the double errors or 3 errors happen. Next we will design our schematics diagram, and we have this one with the hemicycling called schematics in uh, uh, guideline book, and you can do it according to the instructions step by step. But I also would like to show you what I did, make an example. So, and here I strongly recommend you to write down your, like me, like this, kind of this, and your, which is your data, which is the generator phenomena. And here I append the zeros according to the, uh, according to the, here, yes, here is my user data, and I append the 3 bits data, 0. And what after the calculation, what reminder do I get here? So, let's come back to uh, the encoding schematic diagram design. Yeah, here, which is your generator polynomial, which is 1, 0, 1, 1, and we need the uh, 2 XOR elements and 3 D-type flip-flops, and we can see here, use the play symbol to double click it. And as a recommendation, which is the 1G74, which we can use this one. We can use this one, D-type flip-flop, and so make sure your position of the different XOR and according the generator polynomial. So we have here we have the Z and the second power and the three power, and there is no XOR between the second power and the 3 power because it's Z2 has no power here. So, and we can connect them together, use the here, which is the place where, and you can connect them together. And here I made a mistake. Maybe you can show. We must to avoid the junction, so we can just delete the noise and reconnect it. And there is no junction, connect together. And after the generator phenomena finished, and we add one switch to here, and hope it can come back to the Z from the Z 3 power flip flop to the Z, and it will looks like a cyclic, and we can analyze the different division operation time. So first is uh, uh, the first time here, like as the example here, how do we analyze what will happen for the different division operation time, and the start. So for our input, the start will be the append the dot and append 0, which means 1101 and 000. So after our encoding finished, we will get the data and the combined with the reminder, so that we can finish the encoding process. So firstly, we can go to analyze together, and here we input here. First we can input the introduction of the here. We start from the one, the data symbols, and we also here we start from the one, and I input here with both of the XOR, and for the switch, I can do the one, and here we have the D type flip flow, and it stores the how to say the zero state, which means the nothing happened. So we add the both of them to get the first XOR, we get the one, and we pass the one to the cycle, come back to the Z type Z flip flow to one, and the one will be my next state, and the previously there is nothing happened, and for the flip flop, and its storage the zero, and I will use this zero, and here if you here we this the first input of the XOR is the zero, and we already connected to the here past of the one, and we connect with them, and here will be the one, and the XOR result will be one, and we will pass this one to the next state. And here similarly there is the zero state. We will pass with the there is mistake. You will see I did not connect them together, and please pay more attention about this connection, and here we will be in the next state. So it will finish after the cycling cycling calculation finished. We can get our next state, which is the reminder with 110. However, our input here is doesn't work, so we just very simply to pass the one to here. Output also be the one, because here is no XOR calculation. So for the second time at the 2D division operation, and we will transmit here like a second database. But in my case, I have the 110, so my second database will be the 1, and you will see the next state where it will solve in the flip flop, and it will change, and the transpose XOR operation will get the 1, so it will same with the 1, and after the 4 bits calculation finished, we will move to the here, like here we will switch to the next to the control symbols calculation operation division, and nothing will change from here. So the state will, please pay more attention about here the state at the 40 to the 60, and the inside of the state there is no change here, and the next state will be the same. So here I have the same state, same inside state, and it as the 50 time, and I input 0, and here the last state is 0, and the 0 will get the 0, and I pass the 0 to the here, and after XOR operation, it get the 0. So next state will be the 6 0 0, and after that, it also would like to mention about here. After switch, there is nothing left in here. So whatever we cannot contact this part, so the past data will be the 0. So you will see always be the 0 here. Yeah, it should be 0, and there is mistake here I mentioned. So after this one, we can finish this one. So for the last control symbols, append 0, and we will get the reminder with the 1. So we can see for, let's check the last encoding process, and I input the 0, and here, because the last state is the 0 0 1, so after the XOR is will get the 1, and it pass to the here, and with the input we'll get the XOR encoding, we can get the 1. So the encoding process is finished. And let's come back to the guidelines here. So for you, you can I don't know, did you have to do this? And if you would like to do this, and it will help you to understand in detail. Let's move to the decode schematic design. I will show the decode. So for the decode schematic design, you will see here the first step is designing matrix divider schematics, and very similar with the encoding process. We just move to the XOR to the in front of the here, and we don't need to use the switch. And here we need to use the MACJIT algorithm, and it needs 2 division schematics. So we will use both of them, and how to connect them together. Let me show you. And very similarly, you can write your information. Here is my code word, and generate a polynomial and a reminder, and if one error happened, how can I correct the one error? So before the first step, it will very same. We need to use this one to delay the data for decoding process, and buffer register which needed, and you, you will see it can be very long, and you can choose your multiple server in parallel out shift register, and you can use both of them to connect together. And if you don't have enough delay, and you can add more. And here we only have the 7 balls, so 7 symbols. We only need 1 here. Shift register is enough, and it will very same with the encoding process, because we have to get our reminder, final reminder, and after the 7 tax operation like previously introduced, we will get to the last state with the 1 1 1. So we will switch to pass the state with here, transmit to the yes, here we have to step 9. We have to pass the transmit the state to the next D type flip flops in the inside of the. So here I also can get the 111 state, and next we can do the decoding and the reminder. After the decode, after the encoding, so the code word will be a mirror, which means the inside will be the here, and here, which means that we have the first 3 bits, that is the control bits, and the last 4 bits is our data bits. And you will see here there is one mistake at the 6th position. So however, we will read the data from the register. Will from this 1 0 0 1 step by 1 bit by 1 bit to read the data. If we input the 1, and we will pass the according to the shift register to pass to here, and gate no to the XOR, and we have to the part how you say here there is some introduce with the here, as we only know we already can get the reminder with 111. We have to go this part because the 101 is a unique result is the AND gate in this AND gate. So we have to use the basic ignore here. There is mistake for me. I used the previous slides, and we have to move here. But if you can, if your final reminder is here, we will add more. We will add more here. We will add more calculation process in order to reach to the 111, and for last is the 101. So here after so first is the 1, and here that according to the S1 S2 inverse, we have to do the 1 to inverse to use we connect to this inverse the output, and we can get the 0. So the third also be the 1. So according to the AND gate calculation process, it will be the 1 0 1, and the output will be the 1. So no, 1 0 0 will be output will be 0. And previously we have the input here, and it's just a connect to here 0 1. The output will be the 1. And the second position, if we transmit the next bits will be the 0. We already know the here is mistake. So how does the schematic will correct this process, and we process here, and it will be the 1 0 1, and the next state will be the 1 0 1, and we pass the state to the here 1 0 1. So here is 0, and we connect the output with the inverse output, so it will output with the 1 1 1, which means the output which means the output is the 1, and our input here is 0 and 1, 0, according to XOR calculation, and output is the 1. So we correct the error in the 7A7. No, it's it's A2 position. So you can try to your schematic. That is what I want to show you today. Thank you very much.
So, okay, thank you. And yes, what now Mr. Chen showed you, this isn't really in your course project, but you might get some of similar tasks during your last exam tasks. Yes, so your exam task can actually ask you to show operation of one of these schematics. So yes, but again, as I mentioned, by the end of December, you will have these tasks. So at any rate, you will have time to prepare, and you will have option to ask questions later also. So if you don't have any questions now, you can ask when you have these questions. Yes, you're always welcome to ask questions to us. Okay then, so thank you for today's longer than usual lecture. Hopefully you weren't really tired, but well, this was important to finish all in one day. So we will continue in the next week to talk about optimum receivers, how we are receiving these modulated noisy signals, and how do we know where is 1 and where is 0. So, okay, thank you for today, and see you next week.